So in previous lecture, we discussed why we need a synchronization mechanism in implementing multi-threaded program. And because multi-threaded program basically assume that thread scheduler of an operating system, or sometimes it is implemented by user level library. Anyway, the thread scheduler can execute the thread arbitrarily order. Arbitrary order here means that basically by default, there is no ordering constraint enforced across thread. I mean, within a thread, there is an ordering among the instruction, right? There is a sequential order of the instruction. Those ordering is basically kept. That is how each thread get executed. However, among the two threads that concurrently learning, we don't have any ordering if we do not put some mechanism to enforce or constrain possible scenario of their intermixed or interleaved execution. So we need to have a mechanism for programming intended ordering or intended way threads can interact. Otherwise, we cannot enforce atomicity of a critical sections. And if that is not possible, we cannot write correct program. So synchronization is one of the essential aspects in multi-threaded program. And I told you that there can be a various way for achieving that, and various paradigm exist. And some paradigm is better for some application, and some paradigm is better for the other. And I told you that there are tons of different approaches. It's similar to the programming language and programming paradigm. We have a very different programming paradigm, and depending on a situation, some paradigms fit better to some situation and some paradigms do not. And they have all different purpose, and there are all different reasons they exist. In a similar manner, we have a different multi-threaded programming paradigms. And what we are learning is one of the very popular and widely used ones. And I told you that this way of the programming is often referred to pthread programming. Yeah. And in implementing pthread library, yeah, mutex or log is one of the fundamental synchronization mechanism. And when I explain it about some real-world analogy, another word example that share the same intuition as a log in previous lecture. And here, let's talk more technically about a log. I think I already did a pretty detailed explanation on the log, but I'm repeating it. So log is a mechanism that enforces series of an instruction to be executed atomically. Atomically means that either execution is done, never done, or done. But there is no intermediate state about allowed it. So even though there is some non-deterministic thread scheduling interrupt happen, log mechanism is to guarantee that series of instructions to be executed atomically. And log is implemented as a special variable. They are actually a variable. I think if you already checked the pthread tutorial video, then you already saw how to implement, how to use a pthread mutex. Pthread mutex is exactly one of the implementation of a locking mechanism. And in order to use a pthread mutex, you saw that you need to instantiate, you need to declare mutex variable, mutex whose type is a mutex t, right? So it's a kind of a special variable, but the instruction that manipulate this lock variable is different. It should not be ordinary read and write, but lock and unlock operation must be used. Lock and unlock operation must be used. So lock can be contained or can be held by at most one thread at a time. So Lock can be held by no thread. That's good. In that case, we see that the resource that is represented by the lock is free or available. Free or available. So lock is there. So anyone can acquire that and hold that. But if lock is held, it should belongs to only one thread. So to provide mutual exclusion with it. So that it's a special. So so you can think, so here, so let me elaborate it on a little more. So lock variable, since it's a variable, can contain a value, and this value can be either available or acquired, available or non-available. Non-available means that somebody already hold this rock, so the resources resources already acquired it. So we can think the lock variable, so lock n, and it can have a variable available. I represent available as 0 and acquire as 1. So initially, this one is define it as a 0 available, and then what? I told you that thread 1 and thread 2 can check the value of m, but it should not track the value by read operation. Yeah, but it always needs to check the value by log operation. And log operation sometimes referred to acquisition, because this is an attempt to acquire log if it is available. If it is available. So thread number 1 can apply log operation on m. And the behavior of this log operation is that it first checks whether m value is available or not. And in this case, this is available, right? In this case, this is available. So what will happen? It just moving on. This operation just executed successfully, and control flow goes to the next instruction. And at the same time, log value will be updated as a non-available or acquired. And it is augmented as that the owner, the one who acquired this log at this moment, is thread number 1. This information is also attached. And all these steps happen atomically. That's an important point. All these steps happen atomically. So this behavior cannot be implemented by read and write operation, the read and write operation that we ordinarily know. Why? Because ordinary instructions, or if it is ordinary case, we have no guarantee that series of instructions are guaranteed to be atomically executed. But log operation is designed intentionally to be execute all those steps in atomic manner, so that we can use this instruction to provide larger degree of a mutual exclusion. I mean, log operation, this operation itself provide a functionality of a mutual exclusion, because it guarantees series of different steps happening at the same time atomically. So by utilizing this log operation, we extend the scope of the mutual exclusion to a block of the code that is guarded by this log operation. Okay. And moving on. So what happened? So suppose that thread number 1 is executing this some instruction after this log operation, and thread number 2 is also acquiring log m. Then what will happen? It checks the value of the m, and in this case, log variable is not available. It's already acquired. Then what happened? Then it should be blocked. I mean, this operation will be blocked. So control cannot move on to the next step. Why? Control can be moved on to the next step only when this thread, the caller thread, holds the log. and which cannot be satisfied at this moment. So it will be temporarily blocked until when? Until it holds the lock and become its owner. So it will be just a block at this moment. Even if these two operations happen, I mean, even if this lock operation and this lock operation happen right after each other, the second one will be blocked. Why? Because log operation, even if it were 0, if this log operation happened earlier, then what? Atomically, it checks the value of the 0 and updates 1. So in all cases, it is guaranteed that the thread who tracks lock variable being available is at most 1. At most one thread can track lock variable being available. So it will be blocked, and afterward, eventually thread number 1 needs to call on unlock m. Then what? Lock variable turns to 0 and become available. And at this moment, thread number 2 now checks m being 0 and turning it into a 1 and become its owner. And now thread number 2 is holding lock m so that it can successfully move on to the next instruction. Suppose that before unlock, and here lock 2 is, suppose that lock 2 is blocking and waiting for acquired holding lock n. At this moment, what about thread number 3? New one comes in and executes the lock operation on m. Then what will happen? Thread number 3 will also gets blocked because lock is not available. And thread number 1 is releasing lock m here. Then what? And oops. Who will get locked here? Basically, there is no ordering. So as the lock become available again, one of the thread that is waiting for holding lock m will hold the lock and proceed execution. There is no ordering among these waiting threads. It largely depending on the thread library implementation and also some runtime situation of the program that decide who will take the lock in next turn. But basically, we have no rule for deciding who will take the lock next among the waiting thread. 이거 이해돼요? 이것도 규칙이 없어요. 아무나 해도 되게끔 그냥 정해져 있습니다. So suppose that thread number 3 happened to be, it was thread number 3 who will take the lock. In such a case, thread number 2 remains blocked, and thread 3 become an owner of the lock and proceed its execution. Or thread number 2 get a lock and proceed execution, whereas thread number 3 remains blocked and waiting for lock to be released and get the lock, hold the lock in next turn. That's how it goes. Any questions so far? No? Okay, I'm moving on. Okay. So if such lock mechanisms are given, we can nicely use them and we can provide atomicity guarantee of the block of the code through utilizing lock operation. But how can we, but before discussing about how we utilize the lock and implement concurrent algorithm, before moving on there, let's look a little more about how to implement log operation itself. How to implement log operation. Here I brought a piece of the code that become a kind of a naive approach for implementing locking. So how do you implement the lock? We can think in this way. Suppose that we first define a lock variable in this way. Okay, so we here put a flag, and flag can be either 0 or 1. This become a lock variable, and then yeah, we have a API for initializing a mutex. It make a lock 0 to represent it being available. And then what? We have a lock operation and unlock operation. Unlock operation is easy, so let's first check that. What? It just turn the flag into a 0 again. Then it naturally represent lock is available now. And tricky part is lock operation. So how do you write the behavior of the, how do you specify the behavior of the lock operation? In this way, it first checks the mutex value being, flag value of a mutex being 1 or not. And if it is a 1, it means it's not available. So then what? Just spinning on here until this condition to be satisfied, right? And then what? Whenever the flag becomes 0, then it escapes from this looping and turning the flag 1 to declare that this lock is now held by the running thread, the thread who execute this code. Make sense? Yeah, it kind of, it do provide a essence of locking behavior, right? I mean, this is represent the blocking, and this represent, yeah, marking of the flag into unavailable or occupied. So it kind of, this can, these codes represent the basic behavior of the lock operation and unlock operation, but I think you already see this incorrect or something is not perfect for this code, right? Why? What's the problem here? Here the problem is that what? Two different threads can track flag being 0 at the same time and passing on to the line number 11 at the same time. Do you see that chance? For example, do I have an animation here? No, I did. So for example, log is suppose that log flag is 0 and thread number 1, thread number 2, both of them check this variable at line number 9. In this case, both of them check the flag is being 0, and here also both of them see that flag being 0. And then what? After executing this one, what if context switch happens to thread number 2? And thread number 2 also check the flag being 0, and what it does is update the flag by 1 and line number 11. And then at some point, context switching happens again, and control comes back to the thread number 1, and it also checked that, okay, flag was 0, so it already passed it on this loop condition, and then it move on to execute the line number 11 and make the flag 1. Then what? Thread number 2 and thread number 1 and thread number 2, both of them can enter into the critical section at the same time, all right? Because it make a 2 thread being owner of the log at the same time. So this is a wrong implementation. If you really write the code in this way and execute it a multiple time on your machine, then you can easily make the race condition and see this type of thing happens. Do you see? Okay. And then, so what's the problem here? Checking and setting of the flag. Checking and setting of the flag must be happen atomically, but it wasn't happen atomically. So interrupt happen in between, and race condition makes mutual exclusion impossible with this code. So this is not a correct implementation. Then what kind of approach we can take? There are 3. First approach is that instead of doing this kind of stuff, what it actually does is that at log operation, it just disable interrupt. This is a kind of a, and then unlock, it just enable the interrupt back. Do you see this is a, what do you think? Do you think can we achieve the expected behavior of a log and unlock operation by implementing them in this way? Truth is that it does provide the correct behavior, because by disabling the interrupt, it removes the fundamental possibility of having context switching afterward, right? If timer interrupt doesn't happen in any cases, then no context switching happen, because yeah, context switching, especially the preemptive context switching, relies on timer interrupt mechanism. So this will make the code followed by this operation to be executed atomically. So this is a correct implementation. But what's the problem here? There are several problems here. First one is that the foremost reason, so this is one possible implementation of the log operation, but it's not really widely used anymore, because most of all, this is really dangerous. This is a really dangerous implementation. Dangerous in the sense that, what if we execute the log operation, and then at some point, for the region with that we could not consider correctly, properly, program fall into an infinite loop, or program fall into an operation which requires some devices to raise some interrupt. Yeah, if such thing happens, then the whole system becomes unavailable, or whole system went wrong by such mistake, and there will be no mechanism to alternate the execution of the alternate the escape those blocking, because the usual mechanism for escaping some program execution is interrupt. But if interrupt is totally disabled, then system went to be blocked indefinitely. Something went wrong, and something went, there is always a possibility for program to be crashed for different reasons, and there is always a possibility for a program to have a bug. So this approach, this operation, disabling the interrupt, is so risky if the following region of the code is lengthy and it contains some non-trivial logic. So what if after disabling the interrupt, what it executes is only a few instructions that is very clear, then it is all right. Then it is all right. But if it is not, then it is very critical and risky. And especially disabling and enabling of the interrupt usually is a job for the operating system. It shouldn't be a job for the application program. But if a log operation is implemented this way, application program intentionally call on log operation to disable interrupt and exploit the system. So we cannot make such a chance to the application program. So this is not a proper way for providing log operation to the user level program. Makes sense? But I think I already told you this point, but this mechanism is still used for simple embedded system where we are pretty aware of all possible cases, all possible code that possibly executed while disabling the interrupt. And if there is no operating system layer provided for such a small system, this way, disabling the interrupt provide a quick way to make mutual exclusion in a very naive way. So still in embedded programming, this mechanism is used time to time. For a complicated program or complicated system, this approach is rarely used. Yeah, there are more reasons not to use this mechanism. So let me continue on. Reduce the concurrency. Reduce concurrency here means that if we design, even if there is no problem, I mean, if there is no code, buggy code or blocking code that is executed after the log operation, still this mechanism is not to be used because this reduces the chance of the concurrency. What's the big difference from this approach and this approach? You see here that log operation is parameterized with log variable. So even a log operation is executed and acquired a log, that effect is limited to the code that also execute the log operation on the same parameter log variable. So log operation in this form does not globally enforce atomic execution, but the atomicity is a guarantee upon the code that share the same log variable. However, if it happens in this way, you see that atomic execution, sequential execution is enforced globally in a system level. So no other code can be executed at the same time if a certain code is executed on critical section after this type of the log operation. 이걸 좀 이야기하자면 여기서는 log variable m에 대해서 예를 들어서 m1에 대해서 log을 잡고 있으면 다른 스레드에서는 딴 거 execute 할 수 있죠. 예. M1이랑 상관없는 애들, log variable이랑 상관없는 애들 다 execute 할 수 있습니다. concurrency가 있을 수 있죠. 근데 여기서는 어떻게 돼요? 이렇게 하는 순간 concurrency라는 것 자체가 사라져 버리죠. 하나만 실행되게 됩니다. So this is another good idea. A third reason is that, yeah, it doesn't work on multi-core, multi-processor architecture. Why? In multi-core architecture, timer, beside the timer interrupt, it have a natural physical parallelism. So maybe two different logic is executing on two different cores. In such a cases, no matter timer interrupt is disabled or not, there is other code possibly executed on the other core, so that disabling the interrupt does not help enforce atomic execution in multi-processor architecture. Last one, even if there is no problem for the three reasons above, still this mechanism is not favorable because disabling the interrupt is a very costly instruction. So it's not efficient at all. So this should be one theoretic possible implementation, but this is a very far from practical solution. Make sense? Have any questions so far, by the way? If you have a question, just open up your microphone and speak up.
Professor, just to clarify.
Sure.
The reason why this method is so slow is because it's like one stream. Am I understanding correctly?
That is the reason for the second one. I mean, that is what I refer to as a reducing concurrency. But the last one, inefficient here, means the instruction for disabling the interrupt instruction itself is a pretty slow instruction. Yeah, that's another reason.
Thank you.
Okay, good question. Have more questions? Okay, good. Then let me move on. Second approach is very interesting, called software law. In like a 2 slide back, I told you that with the ordinary read and write instructions, it is impossible to achieve the mutual exclusion. That's actually incorrect. Some clever people found a complicated algorithm that use ordinary read and write operation, but implement the mutual exclusion. We call such algorithm software lock, because people call this as a software lock because it does not get any help from the computer architecture. So it's purely implemented with the ordinary architecture with the algorithm. So people call it as a software lock. And there are some algorithm. So let's check this algorithm first. This is a famous software lock algorithm called Peterson algorithm. A bit complicated, but check this together. So we have a flag variable. Flag variable indicate whether flag variable should exist as the number with the number of the thread that involved in the same critical section. So if there are 2 threads, then there should be 2 flags, and 3 threads, there should be 3 flags. Anyway, and the flag variable will indicate whether a thread have a willingness to enter the critical section at the moment or not. And turn variable will indicate which thread is a turn to enter the critical section at the moment. And then initially, so in this example, this is the code for Peter's algorithm of the 2 thread. So this is the 2-thread version. Okay. So initially, it initialized the flag for each thread to be 0, because initially no thread have a willingness to enter the critical section. And then set the turn to a 0, and turn. Here we assume that 2 threads are named as a thread 0 and thread 1. So if the turn is initialized as 0, it means that initially the turn goes to the thread 0. It's a bit weird, but let's see how it is implemented in detail for the remaining operation. Okay. So log operation, what it does is that since this log operation, it first self-declare the caller's willingness to enter the log. So here we have a special variable called self, which return the thread ID. In this case, it will be 0 or 1. If it is 0, it means thread 0, and if it is 1, it means it's a thread number 1. Flag self being 1 to declare that, yeah, these threads have a willingness to enter the critical section. And then what? This is interesting. And then what? What it does is that it set up the turn to 1 minus self. What it means? It, interestingly, it defined the turn into the other ones. So I say that I'm willing to enter the critical section, and then it voluntarily yield the chance to the other one. So I want to use, yeah, so for example, I want to use this resource, declare that, and then what? To the other one saying, this is a very humble action that, why don't you use this resource first? So it just set up the turn into the other ones, and then what? Wait until, and then what? Wait until the other one's flag to be 0. So wait until the other one have a no willingness to use this resource, or what? Come back to itself. So I just read this condition in negative manner. So this one wait, this one fall into wait if flag of the others is 1 mismatch. If the other one also have a willingness to use this resource, it's just a wait. And other one have a willingness to use the resource, and turn is on the other one, then it should wait. But if this condition is not, pass on this blocking condition. And now at this moment, the current thread is holding the lock. This is complicated, but if you carefully write down all different scenarios of this algorithm, then you will find that, yeah, this logic makes sense. This logic makes sense. So for example, if two threads are executing the same locking operation, pretty much the same time, then first one, both of them will declare their willingness, and then what? Passing the turn to each other, then only one of them will have a turn value set to be self, then that one would execute the code and moving on. But if only one of them is executing the log operation, then what will happen? Then it first declare the flag variable, define the flag variable to declare the willingness, and then give a turn to the other one. But since the other one have no willingness to that, the current thread can hold the log, escape from this looping and pass on to hold the log. Interestingly, this algorithm works very correctly. Then why don't we just use this algorithm? Why don't we just use this algorithm? But there's some issue related to this type of the algorithm. First one is that, yeah, it's nicely working and it looks not that complicated for only 2-thread version. But if it should involve a 3-thread, 4-thread, and if it needs to generalize this algorithm becomes super complicated and also super inefficient. There are too many checking and too many waiting, looping, working. So this is a not really scalable solution. But we might think about this for like a 2-thread version. Yeah, so for example, if you're using very old computer architecture, like you're using like a 4-bit MCU, and you need to implement some form of the threading, this might be a solution. But if it is not such a cases, yeah, this one is not a good idea. This one is surely have no benefit in implementing the log operation. Second issue is that I briefly told you that, even if there is a global variable in most of the computer architecture, if one thread is updating a global variable, such update is not immediately visible to the other thread due to the cache effect. And then I told you that for efficiency reason, multiprocessor architecture intentionally allow cache not to be consistent with the main memory for temporal time period. So for many computer architecture, this type of the algorithm hardly works because update on the global variables are not visible to each other. They can enforce immediate update on a memory, but if it is going that way, algorithm becomes far less efficient because immediate update, synchronous update between the architectures and memory reduce the parallelism of the multi-core architecture severely. So that is not a good solution. So software log also exists as a theoretical idea to show that synchronization can be somewhat possible even without extra help from the computer architecture level. Okay, have any question here? This is an interesting algorithm, and Peterson algorithm is the one famous one, and another one is Dekker's algorithm. Peterson and Dekker's algorithm is a somewhat very famous log-free, let's say, software log algorithm. And I think your textbook does not have a much detail on them, but I will give a. So if you check on the Wikipedia page for these two algorithms, you can get more you can have a better understanding on them. I highly recommend you to read on that. Then how actually log is implemented and used with a little help from computer architecture, Computer architecture provide atomic instruction. I told you, we learned that every instruction is atomic, right? Yeah, every instruction is atomic. But this one is especially referred as atomic instruction because it encompasses multiple steps into single instruction, such that they can be executed atomically. So this is especially designed an instruction for providing synchronization of a multiple thread. So hardware here means computer architecture provide, supports. I think the English here is not good. Support checking and setting of a variable to be executed atomically at a single instruction. I will revise this sentence and update the slide and share it among you. So you can think of the architecture provides some instruction that are specially designed, and once you look into semantic of that instruction, you see that read and write happen at the same time. So that read and write are guaranteed to execute atomically. Some special instructions are provided for most of the computer architecture. There are various forms of such implementation, and test and set is one of standard way of one of a very typical example of atomic instruction. Check this one. Note these codes are pseudocodes for describing the behavior of the computer architecture. It doesn't mean that test and set is translated into these instructions. Check this one. It receive a pointer. It receive the address of a variable, and then also it receive a value. So it look like ordinary writing instruction. Write this value on this address. This look pretty much the same as a writing instruction. So what it actually does is pretty much the same. It writes the new value on PTR or the PTR. So it's a kind of a writing or setting. But at the same time, what it does is that it retrieves the existing value that is placed on the address and keep it and return it. So it's a writing, but it have a return value. And once you check the return value says the old value on that memory. So testing means reading, and setting here means writing. Reading and writing happen at the same time. That is what test and set instruction does. So it provides a mutual exclusion of the two instructions, only read and write, but it guarantees atomic instruction of these two instructions basically by utilizing these atomicity. We can implement the locking, and by using locking, we can implement a higher level mutual exclusion. That is something interesting point. So let's read on this implementation of log and unlock. This is actually one valid implementation. And I know that for many computer systems, psled library, once you check on their log and unlock operations definition, then you'll see the similar code. Initially, it have not initially. For data structure perspective, lock variable have a single flag variable. So far, it's all right. And then initially, for initialization step, in make a lock flag 0. 0 means available. And at the log, what it does is that it utilizes this test and set instruction test and set instruction, and what? It updates lock variable into a 1, lock flag into a 1. So if it is a log operation, they want to acquire, if the log is available, they want to acquire it. So they want to write the flag into a 1. So writing will happen, but at the same time, the old value, previous value, or I say the current value, right before this instruction to be executed, will be returned. So if the current value, if the current value is a 1 and it asks to update it into a 1, that what? Yeah, the log is already acquired, so we cannot move on to hold this log. So it'll wait it. Each of this thread should be blocked. This thread should be blocked. So it cannot escape from the while loop. But what if this instruction applied writing on the flag, and the return value of this instruction is 0. Then what? Lock variable, flag of the lock variable used to be 0. So the current thread is reading lock flag 0, and at the same time, lock variable is turning to 1. Yeah, that's the situation. That's what we need to, that's what we want to achieve for log operation. So if that happens, the loop will be escaped and moving on. And the log operation is very trivial. It just to say that log flag is a 0. Make sense? Okay, good. Have any questions so far? So this type of the log operation is often called as the spin lock. Spin lock. We say that this library implements the spin lock with the atomic instruction. So atomic instruction means test and set. Similarly, test and set, the famous atomic instruction is test and set, and very similar yet different instruction is what called it as a compare and swap. Compare and swap. And there are various versions of them. And depending on the computer architecture, the instruction that it provides are different. And some architecture provide a rich set of atomic instruction that can be utilized for different reasons. So for example, atomic increments are also widely, many computer architecture provide atomic increment instruction, which increment the value atomically. I think I already show you kind of a demo for the counter example. Yeah, and spin locking means that here it have a loop. It implement the blocking behavior by looping, right? It just continue looping, continue checking whether the condition is get satisfied or not. So here blocking is implemented by spinning on condition checking. So this way of the implementation is called the spin lock, because the locking operation keeps checking on the lock variable until it finds condition to be satisfied. There are other implementation exists. There is. Spinning is a somewhat inefficient because, yeah, even before, if this thread track the log is currently unavailable and get occupied, is acquired one, it'll be better this thread to be get blocked, not spinning on the variable, but it's just going into the waiting status, as if it is doing the IO for it do the IO operation for external devices. It'll be better for put this thread to be waiting status. However, yeah, if it's just doing spinning in this way, the thread will be remained as an active status or running status. So it'll take some CPU time for spinning, but that spinning will be just wasted, right? Because yeah, no matter how much it spins on there, it does not make a progress, because it make a progress only when the other thread gets to be executed. So spinning is not an efficient way for implementing blocking behavior of a log operation. But still this is widely used because putting a thread to the waiting status is also costly operation, because it involves data structure updates and many scheduling queue updates and so forth. So for simple cases, spinning will provide a better efficiency. And this is easy to implement. And I told you that this can be implemented in this way, even as a user level library. So spin locking is also used. And we will check on another synchronization mechanism called semaphore. And once we check the semaphore, we will have a more, a semaphore is usually implemented not as a spin locking, but by using waiting queue. So at there, we will see a different way for implementing blocking behavior. Okay. So basically, we now have understanding how log operation is implemented correctly. Okay. So our discussion was on locking. And by using locking, we can achieve atomicity, enforcement of the atomicity to our critical section. That's kind of good. But if you really work on implementing multi-threading, you need another need for synchronization. That is to enforce ordering between threads. Mutual exclusion is restricting the interference among the thread, but it does not enforce ordering. So sometimes you want to have a thread number 1 and thread number 2 working on the same variable. For instance, in here, thread number 1 is to initialize this variable, and thread number 2 retrieve the data from this variable. So in such a case, is what? You always want this operation of the thread number 1. I just called it this one as operation number 1, and this one is operation number 2. You always want to enforce operation number 1 should be executed earlier than operation number 2 of a thread number 2. How do you enforce that? By providing locking. No, yeah, it shouldn't happen in that way, right? Even though you put a lock in front of those 2 instructions, yeah, they cannot be executed at the same time, but locking does not mean to enforce ordering among them. Lock is to avoid entering critical section at the same time, but it does not implement enforcing thread ordering. So we need to have a different mechanism. And there are different solutions for this problem. And one famous synchronization primitive used for enforcing the ordering is conditional variable. And sometimes it is referred as a wait and notify. Wait and notify and conditional variables are 2 different concepts, but I think your textbook also address them as the same thing. Yeah, they look pretty much similar. So I just introduce them at the same time. Wait and notify is like this one. We here put an operation wait m, for instance, wait m, and it means that it should wait on some channel m, which I say it's a channel. It's just to wait some channel m. You can also regard it as a receive. It says that I need to receive a message from the channel m. And before receiving the message, the control cannot move on. Control cannot pass on to the next instruction. That's what waiting means. And then what? At here, so even if thread number 2 is the first executed, then thread number 1, it'll block at waiting operation because initially there is no message given. And then thread number 1 execute this code and give a notification, notify M. Notify M. Then what it means is it send the message. Send the message via channel M. Then it give a signal. Then only when, then this signal will be received by thread number 2. So thread number 2 can continue its execution. In this way, we can program thread ordering across threads. Okay, then detailed use cases and also the case that these are used for implementing algorithm will be, you can find some of them from the video tutorial, and also at the next class, I will elaborate it on some log data structure. There, we'll see more details on how to use them to implement some meaningful algorithms. Okay, so here, today's lecture, I introduced you a little more detail about a log operation and how it can be implemented. And also, I briefly introduced about different synchronization mechanism, wait and notify, or conditional variable. These tools are somewhat essential synchronization primitive. And with these two mechanisms, we can program most of the concurrent algorithm that exists today. So we need to learn how to use them and how to exercise them in a proper situation in multi-threaded programming. And that topic will be addressed in next class. Okay, have any question? That's it for today. So if you have a question, I'm welcome to answer your questions.